Hi and welcome everybody to today's lecture, which is titled as Active Physical Layer Authentication. In the previous lectures, we talked about passive physical layer authentication based on physical layer characteristics and hardware characteristics, and we mentioned all these characteristics that can be exploited in order to use them for authentication at the physical layer. In today's part, we will mainly focus on the active schemes of physical layer authentication. And in this case, active authentication is associated with the fact that we add something additional extra to the message we transmit. And we use this extra thing as a way to verify our message, to authenticate our message, or authenticate the party that's sending the message. The steps that we need to follow are summarized in this slide. Step 1, Alice sends a request to Bob for message transmission over a wireless channel. Alice just prepares a request and sends it to Bob for message transmission. Bob receives the request and then checks whether the request is legitimate or not through upper layers authentication mechanism. Then if it's legitimate, Bob generates a symmetric secret key with Alice using a certain key establishment protocol, such as any protocol of public-private key pairs. Otherwise, Bob will ignore the request and stop the communication. In step 4, Bob sends an ACK to Alice for preparing a message transmission. In the message transmission stage, Alice generates a tag, which is shown here in the packet. This is the tag. Let me highlight it for you. This is the tag, this is the message, and this is pilot. So this tag, we added it intentionally beside the message, and this is the tag responsible for authenticating the transmitter. Alice generates a tag based on the secret key and the hash function. This secret key can be upper layer secret key or lower layer physical secret key, which can be generated from the wireless channel, and the hash function to ensure the integrity of the message and make sure the output length is always the same. Then Alice actively embeds the tag into a source message to generate a tagged signal. So a signal message with this tag, with this red part, is called a tagged signal. At last, Alice sends the tagged signal to Bob over a wireless channel. In step 2, Bob receives the signal transmitted from unknown transmitter. Unknown transmitter receives the message. Then Bob generates the tag. Okay, I received this message. The message contains a tag. Bob tries to generate the tag with the help of the secret key. Then Bob detects whether the tag exists in the received signal or not. If it exists and it matches with the reference that Bob has, then Bob accepts the received signal and authenticates the transmitter. Otherwise, Bob rejects it. This is the process of physical layer authentication. Let's see some diagrams explaining these things. So in summary, we have authentication tag over here. And we have the authentication tag. Then we have the superimposed the information message. We superimpose them, the information message with the authentication tag. Then we send them over a wireless channel. Then at the receiver, there is message decoding and authentication tag extraction. Compare it with a local reference tag and make a decision whether if the tag exists and it's the same as the reference, then it's a legitimate signal. If it's not, then it's a fake forged signal. This is the framework for authentication. Okay. Mathematically, the core idea of active physical layer authentication. So this message Where is that? Uh, the message part over here, the message is represented by M, and the tag is represented by T, and this is square root of the power allocated for the tag signal and the power allocated for the message signal, BS and B tag. Why do we take the square root of BS, the square root of BT? Because here the signal is written in the electric field, electric signal. So if it's power, we take the square root of it so that it becomes like current. Uh, so the equations here are always written as electrical signals, not power signals. Electrical signals which represent either the voltage or current. And for the cases when we have R equal to 1, R, the resistance is equal to 1, in this case, V and I are equal. Okay? They are the same. Relatively. Okay, now what happens next? What happens? You have your X, which has the symbol. This is the symbol. And we have the pilot, which is this in the packet. And then you transmit them over a wireless channel. You get this equation. Y is equal HAB. AB is the channel between Alice and Bob, and this is the channel. If we are using OFDM, then it's diagonal in the frequency domain, diagonal, which means you have signals, channels only on the diagonal side of the matrix, and the others are zeros. And this X is the same as this one, which is this message concatenated with the pilot. And why do we need to use the pilot? The pilot is for estimating the channel, for knowing H, estimating it. And then once the channel is known at the receiver uses the channel in order to detect the message. And since our target is to detect the tag here, in this case, we use some equations and formulas in order to find whether the tag exists or not, and then compare whether the tag is the same as the one we have in the reference or not. So tag is contained in R. In this case, we have H0, which means the transmitter is legitimate. The tag is T is not contained in R, H1, which means the tag is the transmitter is fake. I shouldn't trust him or communicate with him. So these are the main things you need to be aware of regarding this technique. And now we will go back to another technique that we presented before for providing physical layer security uh, and confidentiality, and see whether it can provide authentication as well or not. So if you remember with me, when we were talking about confidentiality, physical layer techniques, there is one technique we put it in one of the slides. I think it's in another representation that okay, it's in another representation, but I can draw it for you here. Let's clean this up. We clear all drawing, and here I'm gonna go back to this. And just remember this how it works. Now let's go to yeah, to here, and give you another technique that can provide authentication without using tags. So you have your transmitter here, TX, and you have your receiver, and your goal is to authenticate the transmitter. Like we need to authenticate the transmitter, authentication. We need to provide confidentiality, and we need to also provide resistance to jamming. So we have three problems: authentication. Uh, we need to provide authentication, confidentiality, and availability. This is availability. You can say availability. Availability, we need it to protect our signal from jamming. Confidentiality, to protect our signal from uh, any illegitimate access to our data. And authentication, to prevent spoofing or impersonation, fake transmitters. We shouldn't communicate. So now the technique that I'm going to show you here can provide these three requirements to avoid three major attacks in wireless networks. How can this happen? So here we have the message, or let's say the symbol, the signal S, and on top of that we put another signal called R, which is superimposed signal R1. And this signal is function of the channel between TX and RX H. And then we generate random sequence, randomly, completely random. That's not known to the receiver, and we don't share it with it before. And this is sent to the receiver in the first round one. So imagine we have a jammer who's jamming the signal. So after it reaches here, the signal at the receiver in round one, you will get your signal with other signal R that we intentionally added at the transmitter, and you get another jamming signal here on top of it. This is due to somebody who's jamming our communication. Okay. This jammer keeps jamming. So what you do here at the transmitter decides in this transmission technique to send another packet, and here another packet. So here it was S1, here is 2, R2. So no, here S is the same. You don't change the signal. You just change, instead of R1, you put R2. And this R2 is function of the channel in the second round, and send it to the receiver. And this we put it to round number 2. And the same, the receiver will receive another signal. So this is at time t equal, let's say 0. And at time t equal 1 millisecond, let's say 1 microsecond, you received another packet, okay? And it got R2 in it. And the same, because of the jammer, it receives the jamming signal. So at the receiver, the jammer applies maximum ratio combining process and adds these two signals, like like in an intelligent manner. It tries to subtract these two signals. So after he does the processing, you will find out that the jamming signals in the first round and in the second round, they cancel each other, and R1 and R2 will cancel each other. R1 and R2, they will cancel each other, because R1 is equal to minus R2 almost. When they get added, they get compensated. And the only thing you will be left with is S, the signal. So now, since these R1 and R2 are designed as function of the channel between the transmitter and receiver, as function of the channel, between the transmitter and receiver, they act like a secret key. They act like a secret key because this channel is being estimated at the transmitter and receiver before they start their communication, and it's already to the receiver. And R1 and R2 are function of these channels. So the receiver here will say the following: if after I do the combination, the intelligent processing at my side, if R1 and R2 cancel each other and the interference and the jamming interference cancel each other, and I am left with only my signal S, then I am truly and uh, I am truly communicating with the legitimate transmitter. And this acts like verification, authentication, verification of identity, which is authentication. Plus, since there was R1 and R2 with the signal and these function of the channel of the legitimate receiver, if somebody else, let's say an eavesdropper like this bad guy in between, when he receives the signal is it got R1 and R2, which act like interference, and they are function of the channel. So in this case, he will not be able to decode the signal successfully because he will keep always experiencing interference from the embedded signal at the transmitter. Uh, and if somebody bad like jammer tries to send a signal, he will not be able to stop the communication because the jamming can be cancelled after subtracting the two bits from each other. So the point I want to make here is this is another technique that embeds a signal on top of it and can provide us with authentication plus confidentiality plus availability. Three things in one technique. And here we don't have tags. We don't use tags or anything, and we don't need to know the tag at the receiver ahead of time, which is good in the sense that it saves bandwidth and it reduces complexity. So this is one of the techniques that we usually care about. Now we have something called covered schemes and non-covered schemes. Covered schemes, a covered communication means the transmitter and receiver are communicating with each other in a way that nobody in between here knows that there is communication. It's hidden communication. Where do they hide it? They hide it somewhere, like they hide it in the noise or interference or whatever. So, and this is good for this is applicable for both aware and unaware receiver. This is aware receiver. This is aware receiver that there is communication, the eavesdropper. And this is unaware receiver, doesn't know that there is communication between the transmitter and receiver because the communication is being held in secret. So the negative effect of embedding a tag, like we explained in the previous example, into a source message can be kept under control through adjusting the parameters of the active scheme. So we are embedding a tag, but we don't know, we don't want anybody to know that there is a tag. So if you adjust the parameters properly, you will not make anybody to notice that there is any new thing that you are embedding or adding to your signal. Non-covered schemes, aware receiver in this case, non-covered because the transmitter and receiver are communicating with each other publicly, and the receiver is aware of this, can only be used at an aware receiver rather than at an unaware receiver, which hinders its extensive application. So covered communication schemes are more favorable and more recommended to use in wireless communication because they can provide coveredness for your information where nobody can know there is something going between the transmitter and receiver. So covered active physical layer authentication, we have two techniques. We have the superposition technique that we explained in two examples before in the previous slides. Superposition means Superposition here means that you have something, and on top of that thing, you add something else. This is called in math superposition, superimpose. Superposition, you add something on top of something else. This is superposition. And this is the power domain or voltage. The power and the power is voltage square over R. And I told you if R is equal to 1, this is equal to I square multiplied by R, which is the power. And if R is equal 1, then this I square is equal to V square is equal to the power. This is from physics, electricity physics. So we have another covered active physical layer authentication scheme is called replacement. What do you do in this replacement? As you can see here, you replace certain part of the message with new uh, new tags that can be used for authentication. But these part they act and behave like as if they are information data, and no usually nobody notices that you are changing the packet structure except the legitimate receiver, because he's aware of that and made knowledgeable before the communication starts. The covered active physical layer authentication schemes can be applied to the transmitter identification system, SIMO and MIMO system, and Internet of Things devices. SIMO, you already know, we have, when we say always we have a transmitter and receiver, we mean by that the transmitter has one antenna, the receiver has one antenna, and they are sending their information from these two antenna. But like uh, if you have MIMO system, in this case you have multiple antennas, 2 or 3 or 4, and you have here at the receiver side the same. So you could send the same signal from all the antennas or different signals, X1, 2, 3, 4. So if you send different signals, you will increase the data rate, which is the speed of the internet you can think of, but you will increase interference as well and complexity. If you send the same signal from all the antennas, you will increase the reliability of the system and the range, the quality of your signal, but the data rate will not get improved. I mean, the speed of the internet. So this is what we call MIMO. In this case, all all the antennas receive. Each antenna here is transmitting to all the antennas at the receiver. Same here. Same with this. The signal goes to all the receiver antennas, and the same with this. So you see these interconnection lines. This causes inter antenna interference. And the receiver's job is to be able to handle that, remove this interference links. Because at the end of the day, I want my X1 to be received from by X1 from here, my X2 to be received from this antenna, my X3 from this, my X4 from the fourth antenna at the receiver. But because of the wireless medium and it's not confined, at the end of the day, I don't have a cable that can connect them directly. I'm sending them over wireless, over the air, not through a cable. So this basically will create interference, and the receiver's job is to remove this interference intelligently. This is one of the key problems that we have in communication systems usually. In MIMO, we have some routers at our home that have MIMO, two antennas, for example. So continuing with the non-covered active physical layer security, the non-covered active physical layer authentication can be applied to telephone signal systems, cognitive radio system, and the traditional wireless communication systems. And we have three different cases here. We have modification of the frame structure, modification of the transmission parameters, or encoding of the pilot. So these are the possible three ways that we can play with in order to provide non-covered active physical layer authentication. And if somebody asks us to compare between passive physical layer authentication and active physical layer authentication in terms of metrics, authentication features, advantages, and disadvantages. So in terms of metrics, what do you think of passive physical layer authentication? So it can provide it can provide security and robustness. For active, besides security and robustness, we have covertness. Covertness means nobody is aware that there is communication between the transmitter and receiver. Authentication feature, device-based feature or channel-based feature, channel or device-based, modification of the source message or authentication tag. Advantages, no covertness issue. Here, active physical robustness is independent of the coherence time, channel environment, and user environment because you are embedding a tag here. The disadvantages here, the robustness is determined by the coherence time, channel environment, and user movement because it's completely dependent on the channel. While for active physical layer authentication, you have covertness issues. Do we have a trade-off? Yes, there is trade-off between security and robustness. And for active physical layer security authentication, you have trade-off between robustness, security, and covertness. A trade-off means that you improve something at the price of something else. You don't perform well in all the metrics, but rather in some of them, not all. So this is a brief comparison between passive physical layer authentication and active physical layer authentication. So regarding insights, challenges, and the future directions, um, there are researchers who are working on imperfect channel estimation for physical layer authentication, selection of passive features, robustness, hybrid schemes with passive scheme and active schemes. Like hybrid scheme, you embed two different schemes together, hybrid and passive. Why? In order to furthermore improve the security and authentication process. We have a cross-layer scheme by combining physical layer authentication and upper layer authentication. These hybrid cross-layer, they can provide extra advantages, of course, but they come at the expense of some wastage in time, delay, complexity, sophistication, whatever. Some researchers are applying lessons from NOMA non-orthogonal multiple access to physical layer authentication. Some researchers are studying the effect of very high mobility and the application of physical layer authentication to the emerging wireless systems like millimeter wave system, visible light communication, Internet of Things, body area network, cognitive radio, and GRC. Visible light communication, for example, this is the communication technology that uses light to send and receive data. Another challenge is multi-user communication networks. When the number of users in the network increases, the complexity increases, and the intelligence should be increased in order to handle the interference among them. The application, so We have some studies on the applications of distributed multiple antennas nodes in physical layer authentication. Studies on delay control in mission critical massive type communication, reliable authentication in cognitive radio networks, the application of deep learning in multi-user physical layer authentication. These are the studies that are being conducted related to multi-user communication networks. And we have the Internet of Things network, extending the device-to-device physical layer authentication to end-to-end physical layer authentication. Physical layer authentication handover in dynamic environments such as Hadoop or 5G and beyond heterogeneous network. The integration of physical layer authentication and cryptography-based authentication structure. So all these are studies related to the Internet of Things. And there are some other more studies related to physical layer authentication that we didn't list here that are ongoing as research. So, and there is lots of opportunities related to conducting research in this area and publishing a new material or coming up with new novel ideas that can be patented. But that's it for physical layer authentication. And these are the main things that we wanted to cover in this course. Maybe in the future we can talk in more depth about the mathematical framework behind them. So, as as an example on physical layer security technique, I want you to go to one technique on Google cross-file Mac using ARQ. So, so you can go to this paper and try to understand how we can provide security for confidentiality and then for authentication using ARQ process and how the performance changes and how we can apply adaptation in order to fix this. So this is one of the papers that I will share with you in order to learn the techniques related to authentication and security. This joint FIMAC layer design. Yes, this technique also. So I will share this paper with you. I want you to go through the math there so that you know how to build the mathematical framework behind providing security schemes. Maybe we cannot access it from here, but I have it stored somewhere. I will share it with you and put it in Moodle so that if you have any questions about it, you can ask me in the next coming lectures. So, any questions so far? Everything is okay? Okay,